Besides the ball model, there is another interesting combinatorial model, which is called the lattice path model. Let's look at this picture. The meaning of this picture is to walk from point 0, 0 to some other point. It's not allowed to walk diagonally. Only horizontal and vertical forward steps are allowed. And in each step, you could only move by 1 unit. This is a lattice path model. How is the lattice path model related to combinations? Let's consider this problem. We are going to move from point 0, 0 to point Mn. How many different routes are there? To analyze this problem, if we could only walk horizontally or vertically, we could denote the route by a string in which each character represents a horizontal move or a vertical move. How many steps could we move in these routes from 0, 0 to Mn? M horizontal steps, N vertical steps, and a total of M plus N steps. How many steps among them are supposed to be horizontal? Where are them? We denote it with a string such that each X represents a horizontal move and each Y represents a vertical move. So the string is in the form of XY, XX, YY. And its length is M plus N. And it contains MX. So actually we are selecting MX's from M plus N characters. So the total number of routes from 0, 0 to point Mn is combination Cm plus N. That's the result. You might know that combination is also closely related to Yang-Hui's triangle. Let's look at this picture. Every number in it is actually a combination number. The number in the nth row and rth column is CNR. We also know that every number in Yang-Hui's triangle is also corresponding to a binomial coefficient. So, are binomial coefficients of a plus b to the nth power related to combinations? So next, let's take a look at the binomial theorem. According to binomial theorem, a plus b to the nth power is equal to cn0 times a to the nth power plus cn1 times a to the n minus 1 times b, and so on. So the coefficients are actually combination numbers. Why? Let's analyze it. A plus b to the nth power could be regarded as a multiplication of many a plus b. When we are multiplying them, we are actually choosing a's and b's. For example, in this a plus b, we chose a. And in the second a plus b, we choose b, and so on. For each item in the binomial expansion, a to the n minus rth power and b to the rth power, it means that RB's are chosen from the n a plus b's. So its coefficient is CNR, which is the same as what binomial theorem tells us. So we could see that there is a corresponding relationship between binomial theorem and the combinations. Now, assume that the value of both a and b are 1. By substituting them into the formula, we get that Cn0 plus Cn1 plus until Cnn is equal to 1 plus 1 to the nth power, which is 2 to the nth power. This is an extension of binomial theorem. If we assume that a equal to 1, b equal to minus 1, we would get another interesting formula, Cn0 minus Cn1 and then plus minus until Cnn is equal to 0, as the left-hand side is 0 to the nth power. For different values of a and b, there are different combinatorial identities. This is quite interesting. We could even substitute a and b with different natural numbers to get some interesting result. We've introduced the recurrence relationship of permutation. Actually, there are similar recurrence relationships for combination. Let's look at the Yang-Hui's triangle. We will discover a special property such that the value for each point in the middle is equal to the sum of the 2 points above it. Does it mean that combination has a similar property? we have such a combinatorial identity that CNR equal to Cn minus 1R plus Cn minus 1 R minus 1. How should we prove it? We could prove it with lattice paths. For example, the left-hand side means the number of routes from point 0, 0 to point n minus r. On the other hand, we could classify all the routes by whether the last move is horizontal or vertical. If it's horizontal, the last point is n minus r minus 1 r. If it's vertical, the last point is n minus r minus 1. This means that all the routes from 0, 0 to n minus r are divided into two categories. The first one is to move from 0, 0 to this point, which is n minus r minus 1 r. The second one is to move from 0, 0 to n minus r n minus 1. The number of routes for these two categories are corresponding to the Cn minus 1 r and Cn minus r minus 1 in the right hand side, which is Cn minus 1 r plus Cn minus 1 r minus 1. Now we find that some combinatorial identities could be proved elegantly with lattice paths. Let's look at another one, which is a bit more complex. It looks to be quite complex. The left-hand side is Cm plus nr, and the right-hand side is the sum of multiplied products of combinations. This formula is Vandermonde identity. Vandermonde is an influential mathematician. However, this identity is actually discovered by someone else. Donald Knuth once wrote that this identity is firstly discovered by Chinese mathematician Zhu Shijie, and it is introduced in his 四元遇见 in 3003 years. So we might call it as a true fundamental identity when we will see it again. After introducing the background, let's look at this complex identity, which seems to be quite hard to prove. Let's see what's the meaning of the left-hand side. Cm plus n, r, seems to be choosing r objects from m plus n objects. It seems that the objects are in two categories, with m object in the first category and n object in the second. We choose r objects from them. Let's model it with red balls and blue balls. For example, there are a total of m red balls and n blue balls. We want to choose r balls. This corresponds to the left-hand side. It seems simple to think in this way. Could we also solve it by classification? Among the r balls selected, it might be possible that none is red. There might be one red balls, two red balls, or three balls. According to the number of red balls, we could solve this combination by classification. If there's only one ball chosen, we need to choose only one from m red balls, and then choose r minus 1 blue balls. This is a multiplication of two combinations, Cm1 times Cm r minus 1. This is an item in the right-hand side, so we don't need derived formulas from this problem. We could prove that the left-hand side is equal to the right-hand side only with a reasonable classification. There are a lot of different ways to prove combinatorial identities. For combinatorics, a very competitive task is to research combinatorial identities. Actually, there are also some books specially focusing on combinatorial identities. There are more than 200 combinatorial identities for such a simple concept. we could find a lot of different proof techniques in it. This will be very interesting.